Hi, I'm doing problem of the week number 12. This is problem number 3 from the sheet. So it says find a general solution for this Cauchy-Euler differential equation. So the general solution consists of the complementary and the particular solution, or the homogeneous and the particular. So we're gonna go ahead and take our y's, take the derivative. Let me fix that real quick. Take the second derivative. Then we go ahead and plug that into our equation. Let's call it star. So we plug all this, the y prime and the y double prime, into star. And we go ahead and get the following. We set that equal to 0 because we're trying to find the homogeneous case, or do the homogeneous case. And I went and go ahead and x2, did a little, got the x minus 2 from here, did a little algebra, simplified it, and then my next step is I factor out the xr, and I got this, and using the quadratic formula, plug that in. I got r is equal to 2 with multiplicity 2, and we have a root formula from the book. So our our homogeneous solution is C1XR. Oh, this is the formula. So the homogeneous solution is C1XR plus C2 ln x to the r, and the r's are going to be 2. And since it's multiplicity 2, we have the ln x. So this is our homogeneous case, complementary solution. Now let's go ahead and do the particular solution. So to get our particular, we have x2, y double prime, basically our equation, and I'll go ahead and divide it by x2 to get into the right form, so we could go ahead and actually solve this. So this is what we get once we do that. Alright, so my y1 is x2, my y1 prime is 2x, my y2 is x2 ln x, and to get my y prime of 2, we have to do a little product rule. 2x ln x plus 1 over x and x squared, cancel one of the x's, so you get this right here. Alright, so moving on, we use the forgot the name of it, Cramer's rule. There you go. In order to solve it, we set the first one equal to 0, and then to our forcing function. Unfortunately, there's no annihilators, so we go ahead and run through it. So my y1 and my y2 to my y1 prime, y2 prime, and go ahead and do the Cramer's rule, and the x2 over ln x, we notice that the ln x's are going to cancel, and all we're going to have is the x2, and once you're going to be doing that, you're going to get that negative. This is pretty simple, straightforward. Everything is going to cancel but the x3, as you can see here, so we get that. And then we have just an x left here, take out the negative, do the integral to integrate this to get the u1, and our u1 is negative ln x. Alright, so let's go ahead and do the y2. Same story, since we already did it previously. We know that our bottom is going to be x3 and our x2 times ln x, and this is just going to be 0. There's not going to be a negative, so just go ahead and drop that down here, and x3 and x2 is going to cancel. We're just going to have one x at the bottom, and we go ahead and integrate it, and integrate y2, and it's just a quick u sub. As you can see my steps down here, u is equal to ln x, our du is 1 over x dx, so our x du is equal to our dx. We cancel the x's, we get 1 over u, we take the integral, we get ln u, we plug ln x into our u, get ln of x. So our u2 once integrated is going to be ln of ln x. And this is our particular solution formula. And I went and put my u1, y1, u2, y2 together, and then I simplified it a little bit, and this is my particular solution. Now, our general solution from the beginning of the problem is our complementary solution plus our particular solution. Putting all that together, this is our generalized solution to the DE.